Okay, hello everyone. So, now we start the last and final lecture of this series on cosmology, the sixth one. So, in this lecture we will talk mostly about cosmological structure formation. So, let us define the problem first. As we have seen, the cosmic microwave background observations show perturbations of the order of 1 part in 10 to the 5, and this is at redshifts of 1100. Remember, this was the time when the age was somewhere around 400,000 years after the Big Bang. However, we see today around us that there are galaxies, and the galaxies are coming in groups like clusters, and they are forming walls like this. So, there is a lot of structure around us today. So, the question is, starting from these CMB anisotropies, very small ones, how did we arrive here? How did they grow to form these large scale structures? And that is something which we will discuss today. How do we understand this aspect? The basic idea behind all this has to do with gravitational instability. So, what is the idea? Imagine that you have somehow produced small fluctuations. They can be as small as you want, even 1 part in 10 to the 5 or maybe much smaller than that. So, what has been shown in the cartoon is a plot of density versus, let us say, position in some one direction. Okay. And you can see there are fluctuations in the density. If they were uniform, everything would have been at the mean density, that would be your this black line, but it is not. So, there is this region A which is slightly over dense, there is this region B which is slightly under dense, and C which is over dense, and so on. Now, think about the property of gravity. Just think in terms of Newtonian gravity, that is sufficient in this case. This region, since it has slightly larger mass than the nearby region, it will start attracting mass from the nearby points. So, this region which is already slightly over dense will grow in density because it is attracting mass from the nearby regions, and this region B which is slightly under dense will tend to lose mass. So, from B mass will go towards A and also towards C which is also over dense and preferentially attracting mass. So, after some time what you will find is that these small fluctuations have grown. A which had a fluctuation of at this level has become this which is higher. B which was under dense have become more under dense. So, it will probably go towards something like a void, and C again has become more over dense. Okay. This is known as gravitational instability. So, gravity, its nature is to form instability. So, if you make regions slightly over dense, those regions will tend to just grow in density and vice versa. So, then it is not surprising that in the CMBR sky, if we see fluctuations at the level of 1 part in 10 to the 5, they will grow. Okay. So, that is something which is a given. The question is, can we explain it quantitatively, and can it grow by exactly the amount we see around us today? It should not grow more, it should not grow less. Okay. So, can we work the full thing mathematically and explain the structures around us? Now, the basic thing which is often studied is called the power spectrum. So, we have already talked about the power spectrum in the previous lecture, but let me just repeat what we said. So, remember, the density contrast was defined as rho by rho bar minus 1. Instead of rho bar, I am writing it as angular average of rho, again it is same as average. So, basically this rho angle average would be the average of the smooth, the density of the smooth universe. Delta in principle could be matter density perturbations, which we will be interested in this lecture, or in the last lecture, remember, we were interested in delta of the radiation, because we were doing CMB maps. Now, it is assumed that at least when delta is small in the linear regime, these perturbations are actually realizations of an underlying Gaussian random field. In other words, the probability density of delta is given by a Gaussian form, where sigma tells you what is the width of this Gaussian. Okay. Sigma basically will measure the fluctuations in delta. Remember, the delta, the average value of delta will be 0. You can work that out just from this expression. So, the only thing which matters are the fluctuations or the variance or the standard deviation, the sigma, and that is what characterizes this Gaussian random field. We also saw in the last lecture that it is often convenient to work in the Fourier domain. So, if we take the Fourier transform, then it is straightforward to show that the Fourier transform is also a Gaussian random field. This is if you start with a Gaussian random field in the position space. The mean of this delta, which is a function of k, is 0 obviously, and its variance is essentially given by an expression of this form, where Pk is the power spectrum. In this case, we are interested in matter fluctuations, so we will be talking about the matter power spectrum. Essentially, this is just a more formal way of writing what we already wrote in the last lecture. Basically, you can see power spectrum is something which is proportional to mod of delta square. Okay. So, it is just measuring the fluctuations. Now, the power spectrum is modeled as a primordial part times the transfer function. So, what we say is, because of some quantum effects or something, there was some seed fluctuations and the corresponding power spectrum had a form k to the n. This is something which we wrote in the last lecture, and then there is a proportionality constant, let us call it AS. The subscript S is just to tell you that we are talking about density fluctuations which are scalar fluctuations. There may have been tensor fluctuations as well, we are not going to talk about that, but just to make sure we understand what is going on, let us put the subscript S. Now, there would be many effects which will make the power spectrum change from its primordial form, and all those changes are incorporated through another function called the transfer function, and that is written here. So, the total power spectrum is AS times k to the ns times this t square of k. This part is primordial, this part is what is happening afterwards, and that is called the transfer function. Now, I mean why does this transfer function arise? This arises because the solutions of linear perturbation theory, which we alluded to a little bit in the previous lecture, but we did not go into the details, and we are not going to go into the details even in this lecture, but they tell us that the perturbations at scales larger than the horizon, which means k much smaller than the inverse of horizon size, do not grow, they just freeze to whatever their values are. So, if you are talking about large scale fluctuations, they are not going to grow larger than the horizon size. Perturbations can in principle grow when their corresponding scales become smaller than the horizon, okay. And all scale at some point will become smaller than the horizon because the scales evolve slower than the horizon. Why is this? Now, remember, this is something which we did again a few lectures back. You should have to connect this to, for example, the horizon problem. We were talking about scales evolving as proportional to a and the horizon evolving as either a square or a to the 3 by 2 depending on which epoch you are. So, just go back and remember those lectures and you will understand that the scales evolve slower than horizon. So, at some point, even if you start with the scale which is larger than the horizon, it will eventually become smaller than the horizon or will enter the horizon. If they enter the horizon, if they become smaller than the horizon, in principle they can grow, but now there is a extra complication here. Even at these small scales, perturbation will not grow if you are in the radiation dominated era. They grow, but they grow very little, I mean almost logarithmically. Okay. So, in radiation dominated era, that means no matter at which scales you are, it is very difficult for the perturbations to grow. In matter dominated era, if you are larger than the horizon, then you are not going to grow. If you are smaller than the horizon in the matter dominated era, then only you can grow. So, this is all predictions of the linear theory, not very difficult to work out, but lengthy. You have to go through the perturbation theory in great detail. Now, all these effects, because different modes grow differently, it is not surprising that they will lead to modifications in the primordial part. If all the modes grew at the same rate all throughout, then the primordial form will remain as it is. But because different modes grow differently, that too, I mean, depending on whether they are outside the horizon or inside the horizon, depending on whether they are in the radiation dominated era or in the matter dominated era, they grow differently, and hence you have to introduce a transfer function. Again, we will not have time to work out the transfer function in great details, but let me show you the final result. So, what has been plotted here is the power spectrum versus k. This is basically the form of the power spectrum. The points with error bars are different data points. This plot is slightly old, but the essence remains the same. So, we get measurements of the power spectra from various kinds of observations. For example, the black points correspond to CMB. So, at very large scales, CMB gives you the best constraints on the power spectra, and then you have these galaxies from various galaxy surveys, and towards this part at the smallest scales you have constraints coming from lensing and Lyman alpha forest, and some of these we will discuss, but we will not have time to go into all the details. The solid curve, the red solid curve gives you the theoretical prediction, and as you can see, the theoretical prediction matches very well the data for some preferred set of cosmological parameters. Okay. Now, what do this the form represent? At large scales means small wave number, small k, the form is basically the primordial form, k to the n. Okay. At small scales, however, the form is different, and it does not follow this k to the n form because of the modes evolving differently at different scales, and it has a form which is k to the power n minus 4. So, for example, if n is 1, this part will be proportional to k, this part will be proportional to 1 by k cube. Okay. So, this is how we expect the power spectrum to be just from linear theory, okay, and obviously it matches with observations which come from various kind of experiments. Okay. You can ask what, for example, this peak represents. This peak actually represents the mode, the value of k, which enters the horizon or crosses the horizon at exactly the matter radiation equality epoch. The scales which are larger would have entered the horizon only in the matter dominated era. These scales would have entered the horizon at the radiation dominated era, the small scales. Obviously, the small scale entered first. So, that happened in the radiation dominated era, this would have happened in the matter dominated era, and since perturbations evolve differently in these two epochs, there is a clear distinction in the behavior of these two ranges. Okay. So, this is how the power spectrum roughly looks like. Again, let me say that we did not have time to go through the full mathematics or the derivation, but the basic idea is something I have tried to indicate. Okay. You can work out the mathematics on your own pace whenever you need to. The power spectrum also grows. What I have done here is that I have plotted the power spectrum as a function of k for different redshifts. For example, this is at redshift 6, and then we go to progressively lower redshifts. This is at redshift 0, which is today. So, you can see the shape of the power spectrum roughly remains the same in scales of interest. It just grows, so you have to just multiply by some proportionality factor, which is known as the growth factor. Again, remember, these are all calculated in the linear theory. Okay. Okay. So, the linear theory predictions are quite simple, that there is a shape of the power spectrum and then you multiply by a redshift dependent factor to get its value at different redshifts. As you go to lower and lower redshifts, the overall amplitude essentially rises, it grows. Okay. So, this is the linear growth of the power spectrum. However, linear perturbation theory is not all. First, let us understand that at small scales much smaller than the horizon, the relativistic effects are not that important. So, even a Newtonian theory is sufficient to study structure formation, and that is what we do. We just study structure formation in Newtonian theory as long as we are at scales much smaller than the horizon, and actually most of the time we are there when we want to study galaxies, large scale structures and so on. So, we do not have to worry about relativistic effects for studying a large scale structure around us. The linear perturbation theory, however, is valid only when the perturbations are much smaller than 1. Okay. So, delta has to be like going to 0 essentially. I mean, so that you are able to ignore higher order terms like delta square and so on. So, clearly the linear perturbation theory will break down as the inhomogeneities grow and delta becomes kind of the order of 1. Okay. Now, at that point you may like to work out a full nonlinear theory, but working that out on analytically is almost impossible. It is a daunting task, it simply cannot be done. So, you simply cannot write equations and solve them if you want to work the full nonlinear theory in the most general case. Okay. If you are happy with quasi-linear regimes, quasi-linear means delta is of the order of or slightly greater than 1, but not really too much larger than 1, maybe 2, 3, 4 of that order. Then there are various approximation schemes which one can make use of. One such scheme is very popular in cosmology called the Zeldovich approximation. Again, I am just going to mention this, but we are not going to work this out here. The full nonlinear solution can be worked out if there is some symmetry in the problem. For example, if you assume spherical symmetry, so you say I will consider only a spherical region and work out its growth. Okay, let's say its collapse because of gravity. So, if there is some symmetry, probably it is possible to work out the nonlinear solutions. For spherical symmetry, it can be worked out quite accurately. Beyond that, it starts to become more and more difficult. This is the plot which shows the solutions for spherical collapse. So, for spherical collapse, essentially what you do is you take a region of mass m, you say that is a spherical region, and that is just kind of getting isolated from the rest of the universe and is behaving in its own way. So, we want to study how it grows or how the density grows, how it collapses and so on. So, the basic equation you are going to study is the acceleration equation for the radius, which is, as you know, in the Newtonian theory driven by the simple Newtonian force g m by r square, where m is the mass contained within that sphere of radius r. If there is cosmological constant or dark energy, you may want to put an extra term, and it turns out that in the Newtonian regime the cosmological constant behaves like this. It is a force which is proportional to r and it comes with a plus sign. So, you can see the cosmological constant, as we were discussing earlier, that is something we do not understand at all. And you can see it is a force which is first of all increasing with r, which means it is small at small separations, and it is positive. So, as if its gravity is somewhat repulsive in nature. So, very difficult to comprehend. But in most of the cases what happens is at galactic scales, because r is so small, this term often does not play any important role. So, that is why we do not see effect of the cosmological constant when we, for example, look at our galaxy or even some larger scales like clusters and things like that. Okay. So, often this term can be ignored. So, then you try to work out the solution. In fact, some of this you understand because many of you would have solved some equivalent of Kepler problem and how R evolves in 1 by r square potential. So, what happens is initially R increases. So, this is the time where the sphere is actually expanding with the background expansion. Okay. So, it's as the universe is expanding, this region is also expanding. It keeps on expanding, but since it is slightly over dense, it will start to expand slower than the expanding universe. So, at some point it will start to decouple from the expansion of the universe. So, what happens is expansion kind of velocity slows down and down and down. At some point it stops expanding, it turns around. So, here the velocity goes to 0. So, it has reached a maximum radius and then it starts collapsing. Okay. So, once it starts collapsing, it is giving rise to regions which are ideal for forming galaxies and stars. Okay. So, it goes it keeps on collapsing, and if you just follow this equation, what will happen is it will collapse to a solution where r goes to 0. Okay. It will collapse to a black hole if spherical symmetry is maintained perfectly. What happens in reality, that does not happen, because this perfect sphere where we have assumed that all particles move only radially, what happens is even if there are small tangential forces, tangential motions, so then what happens is as you start collapsing this tangential motions actually gets amplified and they become comparable to the radial motion. So, there is some kind of a randomization happening. So, the whole system effectively what we call virializes. Okay. So, it is not this simple spherical solution anymore. Maybe the overall shape still remains spherical, but inside the particles are moving in all sorts of directions. So, at some point there is a balance between this potential energy and the kinetic energy of these constituents, which could be galaxies or small components within that spherical region, and at that point the system attains a equilibrium and it achieves some kind of a radius and it stays there. Okay. So, this is what I have tried to show here. So, it reaches a maximum radius, it collapses, then it hits a radius somewhere here and it stays constant. By this yellow shaded region, I tried to show a phase which we do not understand this very well. This is randomization, this it is also called relaxation, the way the system relaxes to a stable structure and so on. So, we do not understand this yellow region very well, but something happens here and it achieves this equilibrium position. Okay. So, this is roughly what the spherical collapse predicts. Okay. In the top panel, we showed the evolution of the radius. Now, let us go to the bottom panel, which shows you the evolution of the density of the overdense region. So, you see, if you look at the solid line, that is the evolution of the density. Initially decreases because of the expansion of the universe, it reaches a minimum value, and at this point the region turns around and the density keeps on increasing till it virializes or relaxes, and then it achieves a kind of equilibrium value and it stays there. For comparison, I have also plotted the density for the smooth background universe. So, this is the density which would go and sit in the right hand side of the usual Friedmann equation, and this density simply evolves as 1 by a cube. Okay. So, this line, as you can see, shows you the evolution of the background universe. At very early times, there is not much difference between the density of this spherical region and this background universe, because the departure from the smooth universe is very small. At early times during the epoch of CMB, the departure is 1 part in 10 to the 5. So, you are not able to see the difference here anymore. But as you go, as the density of the overdense region of the spherical region increases, it actually starts deviating from the background, and that is what comes up very nicely in this plot. Also, for comparison, I have plotted the density evolution if you had worked the whole thing out using linear theory. Remember, this equation represents the evolution of the spherical region in the full nonlinear theory, but suppose I had worked out using linear theory, this is the solution I would have got. Again, at early times the linear theory and the solution of the nonlinear theory matches very well, because the density contrast is very small. But as the density contrast starts to grow, the prediction of the linear theory starts to deviate from the full nonlinear solution, and that again is very clear from this plot. Okay. Something which is interesting is you can work out the density contrast when the whole system has kind of virialized and attained this stable equilibrium. It turns out that this density contrast is of the order of 18 pi square, or it is of the order of 200. Okay. Strictly speaking, the density contrast in case of a universe which has no cosmological constant or dark energy in the so called Einstein de Sitter universe, this density contrast at virialization will be exactly 18 pi square minus 1. Okay. But in general it is somewhere around between 150 to 200, okay, depending on how you define the virialization and what cosmological parameters you choose. Suppose you had just worked the whole thing out using linear theory, you can ask what would be the linear density contrast when the system attains this virialization or when the system collapses. That would be given by a number which is 1.686. This number is exactly 1.686 for Einstein de Sitter universe, it is slightly different for other universes like universe which has a dark energy component and so on. Of course, this is all you can do using analytical methods. If you want to go beyond that, you have to actually use numerical methods. For example, you have to study using what we call n-body simulations. So, n-body simulations, what you do is you take a box, you put in some particles and you assume that they are interacting via gravitational force, Newtonian is sufficient. So, you will start with a configuration which is more or less homogeneous, but with slight inhomogeneities put in. Okay. Again, initial conditions statistically consistent with the, for example, the CMBR sky. Then you let the system evolve, okay, under gravity, and this is what will happen. You go around this. So, you can see the system has started becoming more clustered, okay, more patchy. So, there are these overdense regions which you can identify, keep on going, okay, the redshift is decreasing, and by the time you hit redshift 0, you can see the structure which was very homogeneous at early times have become actually quite inhomogeneous and clustered one. Okay. So, you can see there are regions which are very high density and there are regions which have almost no matter like void. Okay. So, the whole thing comes just from the solutions of equations of motion under gravity and of course, expanding universe which is implemented in all these solutions. Okay. You can take a 2D slice of these such simulations and then you can look at it very closely. So, what you see is what we know as the cosmic wave. This is taken from the so called Millennium simulation, which was a famous simulation run like decades back, couple of decades back, but they are still very interesting. So, you can see the overall density field has this web like structure. So, this is often popularly called cosmic web. There are regions which are highly dense. Okay. These are probably the places where the galaxies will form, and then they are kind of joined by all these filaments. Okay. Between these filaments you have these voids, these black regions. So, there are filaments and voids and there are sheets and so on. So, it is a very rich structure with many things which go in here, and it is very nice to study. There are many aspects one can study in these simulations. There are a lot of information which is hidden, and they are really very useful for studying the large scale structure of the universe. Okay. These things can only be done numerically, as you can understand. You can ask, do they match observations? I mean, all these are fine, but what about observations? So, remember in the last even in the first lecture I showed you the kind of observations you see when you look at galaxies around us. You take a slice in the sky, you see all these structures. So, this and these are two slices in the sky showing the observational results. Okay. So, you see all these walls and the galaxies coming together, each point is a galaxy here. Okay. And this come from surveys which are the galaxy surveys which are done. These red one slices come from the simulations, in fact the millennium simulation. Just by looking, I mean, okay, point by point they are different because we do not know exactly what the initial conditions are. In the sense we do not try to explain the structures point by point, but we try to explain the structures only statistically. And you can see visually they look the same. Okay. There are this kind of structures all over, there are these walls which have come across and so on. So, this gives you the first indication that actually the large scale structure as produced by the simulations, at least visually they match the galaxy surveys quite well. You can ask, do they match quantitatively? They do, and that comes because we have already seen that the match of the theoretical power spectrum is quite, it agrees quite nicely with the observational data points. Okay. So, clearly quantitatively these simulations work very nicely. You can go a bit further, you recall that there are peaks in the radiation field, okay, in the radiation fluctuations during the CMB, during the last scattering surface, and these peaks occur at specific values of k, which we had written in the last lecture. These peaks leaves imprint on the power spectrum of the gravitational fluctuations, right. The gravitational fluctuations will also have peaks at these k values and hence on the dark matter power spectrum. So, basically what happens, on top of that what happens is the radiation couples to baryons before in the pre-recombination era when the electrons and photons were scattering off each other through Thomson scattering. This introduces oscillations in the baryonic density field, which in turn can be transferred to the dark matter through gravitational coupling. Remember, the dark matter does not couple to the radiation directly, but it comes in an indirect way. Okay. So, this peak, you can work out what is the corresponding length scale. The corresponding length scale would turn out to be somewhere around 150 megaparsec. Okay. So, that is very large scale, but what it means is that even if we observe the galaxy power spectrum today, if our theory of structure formation is correct and if the CMBR observations indeed give you the positions of the acoustic peaks, then we expect similar oscillatory nature, similar peaks in the dark matter power spectra, in the power spectra of the large scale structure even today at 150 megaparsec. The amplitude of the peaks would have come down drastically because there is nothing which are sourcing them, but whatever imprint it left at that time is still there. These peaks in the galaxy power spectrum in the large scale structure are known as the baryonic acoustic oscillations, BAO. Do we observe the BAO? Indeed we do. So, what has been plotted here is the power spectrum of the galaxies versus k, and it is appropriately scaled, a smooth component has been taken out. So, if there were no baryons, if there were no such peaks, you would have expected this quantity to be 1 throughout. But you can see the data points which are given by these error bars are large, but you can still see it clearly shows signature of oscillations. Actually, what you should look at is in the right hand side, because the left hand side is a kind of raw data and then you apply some corrections to get to the actual predictions in the right hand side. And if you forget the solid line for the moment, just look at the data points. The data points clearly show evidences of oscillation. So, this is the detection of the baryon acoustic oscillations, and this tells you that our theory of structure formation starting from the CMB sky to today is indeed correct. Okay. So, there is something which we see in the CMB sky and the same imprint is now again seen today in the nearby galaxies, and there must be something which has happened in between which we do not see every phase in detail, but this is something which we work out using theory and we predict this, and it turns out that it matches the observations. Okay. So, the prediction is the black solid line, and you can see it matches the data points quite well. So, this is a big success for the theories of structure formation, the fact that we can now understand how the large scale structures formed starting from CMB, and let me just iterate again, the basic concept here is still the gravitational instability, okay? And then everything else is details of the mathematics and so on. Okay. Now, are all is this all about the cosmic structures and so on? Can we do a bit more? In fact, if you look at the simulations, what you see is there are these places which are these dense structures. These dense structures are what? I mean, in the spherical collapse language, these are structures which were initially expanding with the universe, then they turned around and collapse and become very dense, and these are the points which are there. But in between that, you can see there are a lot of places where the densities are not very high, and there is quite a bit of matter here. Now, these regions are known as the intergalactic medium, because this is a medium between these collapse structures, okay, between these high density regions. You can ask what is the relative mass in these high density structures where galaxies will form vis-a-vis the intergalactic medium. So, what has been plotted here is the fraction of mass versus redshift content in halos of different mass. Okay. By halos I mean these collapse structures. Okay. And I have plotted this for halos of different mass starting from 10 to the 4 solar mass to 10 to the 12 solar mass. 10 to the 4 solar mass are very small halos, okay, which would have formed at very early times. So, if you look at the solid line, this is for 10 to the 4 solar mass halos, and you can see at early times when redshifts are high, basically they dominate the matter budget in collapsed halos. And then at later times you can see the heavier halos starts to come into the picture. So, for example, at early times there is no mass in 10 to the 12 solar mass halos, which is this line, okay. But at lower times the mass is dominated by this heavier halos. So, this is known as hierarchical structure formation, where small halos form first and they merge and form larger halos. Okay. So, at early times you have smaller halos, at later times you have larger halos. Nevertheless, you can ask what is the fraction of mass which is contained within the halos. For that you have to look at the values in the y axis, and you can see the typical values are like 1% to 10%. Okay. At early redshifts the values are smaller. At lower redshift you can see the values are higher, but still we are talking about somewhere around 10%. So, only 10% or less of the mass is contained in this collapsed or high density objects, which will eventually form galaxies and stars. 90% or more of the mass is actually in the intergalactic medium. Okay. So, intergalactic medium is something which is diffuse, which is low density, which will not form galaxies, which do not emit any luminous light or anything, but they contain most of the mass, okay, because they are spread over large volumes. Okay. The galaxies and the intergalactic medium are very closely connected, because at early times all the matter is in intergalactic medium. So, in that sense the galaxies are formed out of the intergalactic medium. Now, gas in the intergalactic medium can be accreted into the halo, then converted into cold gas in galaxies. So, this is the connection between intergalactic medium and the so called interstellar medium. Similarly, there could be energetic effects within the galaxies like galactic winds and outflows that can eject gas from the galaxy, from the interstellar medium into the intergalactic medium. So, the galaxies in the intergalactic medium are constantly interacting with each other, and so ideally if you want to understand galaxies and other structures, you have to understand intergalactic medium as well. How do we understand intergalactic medium? So, one popular way of probing intergalactic medium observationally is through what we call absorption lines in the spectra of background source of light, for example quasars. So, we study quasar absorption lines. So, there is a background quasar, light is coming towards us. While the light is coming towards us, it is passing through the intervening gas in the intergalactic medium, and that gas produces absorption signatures in the quasar spectra. For example, if there was nothing between the quasar and us, you would have observed a spectra which looks like this, the line, and it would have gone like a power law here, okay, this dashed line. But what you see is lot of absorption, and that is happening because of the material between the quasar and us, mostly the intergalactic medium, because this line of sight very rarely passes through a galaxy or a halo. So, that is how we study the intergalactic medium, okay, quite interesting in that sense. Now, this is a spectra of a quasar, okay. So, a quasar spectra in absence of the intergalactic medium would look like what is shown by the blue line, but you can see there are a lot of features. Now, the absorption features here basically arise because of Lyman alpha transition of neutral hydrogen between the quasar and us. Lyman alpha transition is when the neutral hydrogen atom, the electron is in the ground state, it absorbs a photon and goes to the first excited state. So, it is basically n equals to 1 to n equals to 2 transition, that is called Lyman alpha, and if the photon is absorbed, you do not get it. So, that produces an absorption signature. Okay. Clearly, this absorption happens because of neutral hydrogen. So, you can also see there are regions where there are no absorption, like this region, okay. There is no absorption here. Okay. So, the regions where there is no absorption will correspond to either ionized regions, which means there are no neutral hydrogen, or probably no matter at all, which is unlikely. Okay. Now, what can be done is this Lyman alpha transition, its cross section and other properties are very well understood from basic quantum mechanics or atomic physics. Okay. You can work out that the absorbed radiation will be the unabsorbed flux, which is this blue line, times exponential of minus of a factor which is roughly 10 to the 5 times the neutral hydrogen fraction. Okay. X H1 gives you the fraction of hydrogen that is in neutral form. Okay. So, it is a dimensionless quantity giving you the fraction of hydrogen that is in neutral form. Okay. Now, imagine then this XH1 to be, if you say everything is neutral, let us say you start with that, then XH1 will be 1. In that case, the absorbed flux will be attenuated by a factor which is e to the minus a huge factor. Since the exponential is a very strong function of its argument, this will essentially give you a 0. Okay. In fact, even if XH1 is, for example, 10 to the minus 4, this factor will turn out to be something of the order of 10. E to the minus 10 is still a very small number, and you would have still got a absorbed flux which is 0 basically. Okay. But what you see, so 0 would look like this green curve. Okay. You would have seen something which has nothing is coming to us. But what you see is all these features. Okay. There are regions of absorption and there are regions of no absorption and less absorption, more absorption and so on. You definitely do not see anything which looks like the green one. The fact that you do not observe something which looks like the green curve tells you that the neutral hydrogen fraction must be 1 part in 10 to the 5 or even less. Okay. So, that this factor in the exponential is not very large and you do not absorb everything. Okay. So, this is a very strong result. Just by looking at the spectra, you are telling that the universe here is actually very highly ionized. Okay. Only 1 atoms out of 10 to the 5 is in the neutral form, everything else is ionized. Okay. So, basically that is telling you that the universe is more or less in the plasma form, the intergalactic medium is more or less in the plasma form. This is related to the cosmic reionization which I talked about, which is very crucial while also interpreting CMBR observation. So, the idea is, as you know, the universe became neutral, the neutral atoms formed at redshifts of 1100 when the age of the universe was just few 100,000 years. However, at lower redshifts below 5.5 or so, the quasar absorption lines experiments of the observations show that the universe is very highly ionized. This is something which I just discussed. So, something happened in between that the universe got ionized, and as per our current understanding, this is happening because once you form stars in the universe, the photons come out of these stars and galaxies and ionize the surrounding medium. That is known as cosmic reionization, and that is basically what is being observed in this quasar absorption system. So, reionization is something which is a direct consequence of the formation of the first stars. So, this has gathered a lot of interest in the field in recent times, where people want to understand the early structure formation vis-a-vis when the first stars were formed and so on, and using that explain and try to tie up various observations. So, you can already see that reionization already connects to different types of observations. One is CMBR, which I talked about in the previous lecture, and one is this quasar absorption systems, which is a very different kind of observation. Okay. Both have reionization somewhere built in between. Now, one can do various modeling where you do reionization by stars. For example, this is a realization of that cosmic web in slightly low resolution. So, there are places where galaxies are going to be formed, and once you form galaxies, you are going to ionize the surrounding region. So, when you ionize, there is no neutral hydrogen there. So, it will look as black. Wherever there is neutral hydrogen, it will show up in some color. So, as you see, as you go along, you will see that the universe is getting more and more ionized. Okay, more and more regions are becoming black, and these black regions are growing, overlapping, and at some point almost the bulk of the universe is ionized. So, these come from our understanding of reionization. So, these are basically some simulations we have been doing, our group has been doing, and this gives you some idea about how reionization progresses. Okay. There are lot of upcoming experiments which are planning to study this reionization and also the early galaxies, which are quite interesting. So, one which is experiment, which is a satellite, which is a kind of upgraded version of the Hubble Space Telescope. It is known as the James Webb Space Telescope, JWST. It will go up probably next year or in 2020, and that is going to directly observe the first stars in the sky. And in the somewhat far future, there are other telescopes which are quite interesting, particularly for India. For example, India is involved in a project called 30-meter telescope, which are kind of next generation of optical UV and infrared telescopes, and there will be these will be very large telescopes which have power to observe these very faint galaxies at very high redshifts at very early times, and they will settle the issue about when these first galaxies form and how did the reionization occur and so on. They will also observe the low redshift universe at much more sensitivity, with much more sensitivity, and very nice science which will come up. There is a different way of probing this reionization, that is through directly observing hydrogen and basically the hyperfine transition of the hydrogen and the 21 centimeter radiation from that. And that will be done by another project called the square kilometer array. This is an array of radio telescopes, and again this is something where India is involved. So, these are two international mega projects where India is involved big time, and both of them will have lot of answers to many cosmological problems, and in particular something I told you about, which are the early galaxies. So, this is all I had to say about cosmology in these 6 lectures. So, if you have followed these lectures, you would have understood a bit about the Big Bang model, its success stories, the fact that it can explain the formation of nuclei, the formation of the CMBR, the expansion of the universe, and also the structure formation. It can not only predict observables, it can also help in constraining cosmological parameters using observations as well. So, in that sense, this model has been very successful, the theory has been very successful. There are a lot of features which I unfortunately did not have time to go into, but hopefully there will be enough suggested reading material accompanying this course, which you can go into if you are interested more. So, let me stop here and thank you for your attention.